Hello guys, welcome to my channel. So we are going to discuss today the penalty approach for solving the question related to FEM, that stands for finite element method to solve the questions. So I'll be quickly going through the basic concepts that are required to solve these questions, and then in the next videos we will be discussing some problems as well. So this will be a very short video. So technically there are two sort of axes. One is global axis and other one is local axis. So global axis actually represents the overall axis of the whole structure, while the local axes are related with the particular element axis. So let's see how we will be differentiating these stuff. So in the FEM, let's suppose we have two elements. I have represented black and red elements. Element 1 is represented with the black and the element 2 is represented with the red one marker. So in FEM, the basic stuff that you need to know is like the elements are represented with the encircled numberings, while the nodes that are important stuff as well that are represented with the simple numbers like 1, 2, and 3 kind of stuff. And you need to also remember that each element has two nodes. For example, this element number 1 has two nodes that are 1 and 2, while the element 2 has two nodes that are 2 and 3. So these are also important. So the other stuff is like whenever you will be representing the whole structure stuff, that you will be representing in the global axis zone, and that will be represented in the capital letters, like stiffness matrix is represented with the capital K, then the nodal displacement matrix is represented with the capital Q, and then the force method is represented with the capital F. While the local axis stuff, for example, for the element 1, if you want to represent its nodal displacements or its stiffness or its loading stuff, that you will be representing with the smaller letters like K, Q, F with the small letters. So this is one stuff to understand. The second stuff is also the overall size of your matrix is normally the size of matrix is made up of number of rows and number of columns, and those number of rows and columns depends on the number of total nodes that are given in your question. For example, in this example we have three nodes, so the total size of our global stiffness matrix will be 3 cross 3. So that is another important stuff. The last thing to understand before you start your question solving question is to identify what are the common nodes between the elements. This will help us in developing the global stiffness matrix. For example, if you see here in this example, number 2 node that is represented here, that is actually showing us the common point. So number 2 node is common between two elements. So these are important stuff to understand first of all. Then we will move towards the basic question strategy. So the basic question strategy stands simple like KQ is equal to F. So K represents the stiffness matrix, Q represents the nodal displacement matrix, and F represents the nodal force matrix as well. So first of all, we need to develop the stiffness matrix. For developing the stiffness matrix, we need to develop stiffness matrix for each element separately. So for example, we got two elements. So one element is this one, other one is second element. And for each element, normal stiffness matrix for, I'm just talking about at this moment, the local stiffness matrix for each element. For each element, the formula for like the matrix represents like first like stiffness K1, K12, K2. So these are one are representing here the locations of positions of each matrices, while their quantity will be equal to summation of Young modulus, that's a material property, then area, that's a geometrical property of the section, and then it comes as the length subtracted division by the lengths, that will be the length of each element. So similarly you will find K for first element, that will be E1 A1 divided by L1, and then from this value you will be filling up this matrix that will be represented like this way, like two negative signs on the other diagonals and both positive on the right diagonals. While for the second element you will do the same stuff. Sorry, I have written here positive, but these two elements will be negative as well. So what you will be finally doing, you will be finally combining whole these two stiffness matrix in the global stiffness matrix. So you will be writing 3 by 3 stiffness matrix, because 3 global no, three nodes were there, so accordingly we will be adding all them. So these four will be written here while these four will be written here. So since we identified initially the number 2 node was a common node for us, just like here we have mentioned, uh, just like here number 2 is a common node, so obviously the matrix that is corresponding to number 2 node will be added for both elements in the global stiffness matrix. So here we have added both of them, so this becomes our global stiffness matrix. So FEM is very simple till this point, but now comes here the penalty approach. So what is penalty approach? So understand penalty approach, let's look at this form. So let's see, this is a wrong example. So in the penalty approach, what we normally do, we replace our sport with some spring and giving a value of spring as C, calling that spring has a stiffness as C. So what is this C? C value is a stiffness that we are assuming that should be equal to the maximum stiffness of all the members, like element stiffness that we are getting. So element stiffness is coming from the global stiffness matrix. So what we will do, we will take value of C will be the maximum value out of that stiffness matrix. So if we'll go through this global stiffness matrix, that is the initial global stiffness matrix, so the C value will be the maximum out of these values, and I'm gonna give you a hint like this maximum value will always be located on this diagonal axis, because if you see the common nodes are always located here, so we are adding these stuff. So you can take the maximum value out of this one and then you will multiply it with 10 raised to power 4 to get the proper value of C. Since now you got the value of C, that is a stiffness for your according to penalty approach, then you need to add this value of C in the global stiffness matrix wherever your sports nodes are. So if you see your actual problem, your sports nodes are at 1 and 3. So what you will doing, you will be adding these C values in the global stiffness matrix that will formulate the final global stiffness matrix here at point 1 and 3. So that will do for your sports purpose, like your where your sports are there. So sports were located at 1 and 3. From there you got your C values and you put it here. So obviously at we are going to say there, like at these ends we have the maximum stiffness of our sports. So once you have global stiffness matrix, the 10th question becomes so simple. Like what we need to do now, we got the K value. So finally, now what we'll be doing, now we'll be writing the Q matrix. That's a nodal displacement matrix. Then we'll be writing the force method. So here, if you see in the main question, I have just supposed a load P in the second node in a positive direction. That's why in the force method, only in the second node we have placed the force P. So now we'll be writing the final equation, that is KQ over equal to F, and Q, the nodal displacement matrix, will be equal to inverse of stiffness matrix, that you can solve with the help of calculator as well as the Excel, Microsoft Excel you can use. If you got any problem with this solving, you can comment and then I can fix those stuff as well in some separate short video. Then you will be getting this nodal displacement matrices that will be results given to you, and then the values that you're getting, it means like q1 at node 1 you have this quantity of displacement, at node 2 you have this displacement, and node 3 you have this displacement. And finally, once you have nodal displacements, you will be multiplying that nodal displacement with the C value that you have got earlier to get the reaction. So it will be a stiffness multiplied by displacement will give you a force, that is actually reactions at end 1 and as well as at end 3. Finally, this is reaction, that is your nodal displacement, and finally when you need the stresses, stress is equal to Young modulus multiplied by strain, while strain you already knew it's equal to change in length divided by original length, while the original length of the element you will write down, while the change in length will be equal to nodal displacements multiplied by these matrices. So this is the formula for B, and then you will be replacing L with the original length of the element, while you will be multiplying Q with this matrix to get. So remember, sigma 1 is for first element, and first element was made up of node 1 and 2. That's why q1 and q2 will be written. And for the second stresses element, for second stress 2 stresses for second element will be like, for it's comprised of node 2 and 3. That's why nodal displacements for 2 and 3 are used to calculate the stresses. That's how you will be solving this whole question of FEM with one dimensional problem using penalty approach. So if you got any queries, just let me know in the comments. I will tackle those one, and in the upcoming videos we'll be discussing a couple of questions related with this whole penalty approach.